Hello my friends and welcome back to the Today Machine channel. This automatic brick-making machine is designed to efficiently produce large quantities of bricks with minimal labor. Here's how it works. Step by step. Box feeder. The process begins with the box feeder, which automatically feeds clay into the system. This ensures a consistent and regulated supply of material to the next stage, minimizing interruptions. Roller mill. The material from the box feeder is passed through the roller mill, which grinds and crushes the raw material into a fine powder. This step ensures the material is properly conditioned for shaping into bricks by removing any larger aggregates or impurities. Extruder and mixer. The powdered material is then fed into an extruder, where it is mixed with water to form a homogeneous, plastic mass. The extruder shapes this mass into a continuous clay column through a mold. This column has the required dimensions of the brick. Brick cutter. Once the extruded clay column reaches the cutter, it is sliced into individual bricks of uniform size. The brick cutter can adjust the length of the bricks as needed, ensuring consistency in production. Automatic brick stacker. After cutting, the bricks are automatically arranged and stacked by the brick stacker, reducing the need for manual labor. The stacker positions the bricks in an organized manner, making it easier for drying and firing. This machine can produce up to 5,300 bricks per hour. Its high efficiency, combined with the automatic stacking feature, significantly reduces labor requirements, boosting productivity and ensuring uniform brick quality throughout the manufacturing process. The fly ash brick machine with a 12-cavity automatic mold is designed for efficient and high-capacity brick production. This machine features an advanced automatic system, enabling the consistent production of 16,000 bricks per shift. With a 12-cavity mold, it can produce multiple bricks simultaneously, improving output and reducing manufacturing time. The use of fly ash in brick making is both cost-effective and environmentally friendly, as it utilizes industrial waste materials. This machine is ideal for large-scale brick production, offering precision, durability, and ease of operation. The poly-level system is an innovative alternative to traditional mudjacking for raising sunken concrete slabs. When slabs on patios, sidewalks, and driveways sink due to soil erosion or settlement, the system offers a more efficient and advanced solution. Traditional mudjacking involves drilling large holes in the slab and injecting a heavy mixture of mud and cement beneath to lift it. This method often adds excessive weight, increasing the chance of further settlement. In contrast, the system uses a high-density polyurethane foam, which is much lighter at just 4 pounds per cubic foot compared to the 120 pounds of a mud-cement mix. This lightness reduces stress on the soil beneath. The process begins by drilling small, dime-sized holes into the slab. Through these holes, the polyurethane foam is injected. The foam expands, filling any voids or gaps in the soil, and gently raises the concrete slab to its original level. The expanding foam also reinforces the soil, preventing future erosion and settlement. Polylevel offers additional benefits over mudjacking, such as faster installation and reduced downtime. Within 15 minutes of installation, the concrete is ready for use, allowing homeowners to walk or drive on it almost immediately. There's no extended curing period, making it a convenient and durable solution for fixing uneven concrete surfaces. The sealing of pipe and cable penetrations using Driffle follows a precise process to ensure effective insulation. Before applying the sealant, the area around the pipes or cables must be cleaned of dust, grease, and moisture. Driffle can be applied in temperatures ranging from 18 degrees Celsius to 50 degrees Celsius. Once applied, it remains effective in temperatures as low as -40 degrees Celsius and as high as 180 degrees Celsius. Before sealing, ensure that the distance between the individual pipes or cables, as well as between the pipes and the wall, is between 4 mm and 150 mm. Place filling material around the cables to maintain this distance. Additional fillers may be used if needed to achieve the correct spacing. Next, use a hand press or an electric cartridge gun to apply Driffle. Start by inserting the nozzle at least 3 cm deep into the opening, ensuring that the nozzle remains within the sealant during application to avoid air pockets. Fill the cavity from the bottom upwards in a dense manner. If necessary, use additional cartridges to complete the filling. Driffle adheres well to all surfaces. Once applied, smooth the sealant with a spatula or a damp cloth. The seal is fully load-bearing after 24 hours. To calculate the exact amount of sealant and filler needed, use the calculator available on the PipeLife website under the Downloads section. Further details on processing can be found in the installation guide. Building a walkway with the Quikrete Walkmaker is a simple DIY project that can be completed in a few steps. Begin by preparing the site, removing sod or soil, and leveling the ground as needed. With minimal surface preparation required, the Walkmaker can be placed directly onto the ground. Use Quikrete crack-resistant concrete mix, which is fiber-reinforced to reduce shrinkage cracking. Mix 180 lb. Bag of concrete per Walkmaker form. For a decorative touch, you can add Quikrete liquid cement color to the concrete mix. Blend the color into the water before mixing it with the concrete for uniform results. Place the Walkmaker form on the ground and fill each cavity with concrete, pressing it in with a margin trowel to eliminate voids. Once filled, smooth the surface and immediately remove the form. Rotate the form slightly to create a varied pattern as you continue along your path. Allow the concrete to set for about an hour before smoothing rough edges with a trowel. To cure the concrete, apply a fine mist of water over 3 to 5 days, or use Quikrete acrylic concrete cure and seal, which adds protection and a semi-gloss finish. The Quikrete Walkmaker is available in various patterns, making it easy to customize your walkway. You can complete the project over a weekend or tackle it one section at a time. This is a fly ash brick making machine in Odisha. It is designed for efficient, high-volume brick production, with a capacity to produce 10,000 fly ash bricks per shift. It operates by combining fly ash, cement, sand, and water in precise proportions to form a uniform mixture. This mixture is then fed into the machine's hydraulic press system, where high pressure is applied to mold the bricks. The machine ensures high accuracy and consistency, producing bricks with guaranteed strength of 11 N per square millimeter, or 110 kilograms per square centimeter. Its automated features and user-friendly interface make it easy to operate, minimizing manual labor while maintaining high output quality. The bricks are ejected and stacked for curing after being molded. To repair cracks in vertical concrete surfaces using Quikrete, the first step is preparing the crack properly. Using a chisel and hammer, widen the crack to at least 1/4 inch to ensure proper adhesion of the repair material. This also helps remove any loose or deteriorating concrete. The edges of the crack should be vertical or beveled into an inverted V shape. Once this is done, clean out any remaining debris with a brush. For cracks less than 1/2 inch wide, Quikrete textured acrylic concrete repair caulk is ideal. This product is designed to blend with the color and texture of the concrete, making it suitable for cosmetic repairs. It can be applied on both vertical and horizontal surfaces, and once it dries, it forms a durable, long-lasting repair. To apply the caulk, cut the tip of the tube at an angle, matching the width of the crack, and load it into a standard caulk gun. Slowly draw the gun along the crack, ensuring the caulk is forced deep inside. Immediately after applying, smooth the caulk with a trowel to match the texture of the surrounding surface. The repair will start to form a skin in about 20 to 40 minutes and harden fully within 1 to 2 hours, depending on the temperature, humidity, and crack depth. Paving stones are available in a variety of colors and sizes and are known for their strength and durability. The first step is to mark the layout of your patio. Using spray paint, outline the perimeter of the area where you want your patio to be. Plan the layout, taking into consideration the desired height of the pavers and their direction. To ensure accuracy, place a string line down the middle of the outlined patio, tying it to stakes on opposite sides. Use a 3, 4, 5 triangle to confirm that the string is perpendicular to the house. Once your layout is set, establish the height of the pavers. This should be slightly higher than ground level, sloped away from the house to allow proper drainage. Use a line level to ensure the string line has a slope of about 1 inch per 8 feet. With your project area marked, it's time to excavate. Dig to the necessary depth, adding 6 extra inches beyond the string lines. Remove the grass using a sod cutter or spade, and shovel the soil out. Regularly check the depth using a tape measure. Once the area is clear, install a base layer, using around 4 inches of well-compacted paver base. Tamp it down with a compactor and lightly wet the base to ensure it's firm and flat, maintaining the proper slope. Next, prepare the sand bed. Lay steel conduit pipes on the base to act as guides, and screed the sand between them using a 2x4 until it's smooth. Remove the pipes and fill in the gaps. Avoid walking on the sand, as impressions can disturb the smooth surface. Begin laying the stones, setting them down carefully without sliding them, as this can disturb the bed. Continue laying stones outward in a triangular pattern. If needed, cut the stones using a masonry saw with a diamond-tipped blade, Once all the stones are laid, install plastic edge restraints around the perimeter and secure them with landscape nails. Finally, use a vibrating plate compactor to set the stones in place. Sweep paver sand over the area to fill any gaps and compact the surface again. With your patio complete, you can now enjoy a beautiful outdoor space, designed and built by you. With over a century of experience, Gaeaforce has evolved into a leading manufacturer of ceramic floor and wall tiles, producing more than 2.5 million square meters annually. The factory, which spans 160,000 square meters, integrates cutting-edge technologies, ensuring that all products adhere to the highest quality standards. The ceramic manufacturing process at Gaeaforce consists of several critical stages: preparation of raw materials, pressing, glazing, firing, sorting, and packaging. Each stage is meticulously designed to ensure consistency and quality in the final product. Raw material preparation. The first stage of the ceramic manufacturing process is the selection and preparation of raw materials, which include clay, feldspar, sand, carbonate, and kaolin. These raw materials form the base of the tile, known as the biscuit, and the glaze, which is applied to the surface to create various designs. The raw materials are subjected to a mechanical milling process to disperse particles and reduce their size. This milling ensures the desired particle size and texture, creating a homogeneous mixture. Once the raw materials are milled, they are fed into an atomizer for spray drying, which converts the mixture into fine, spherical dust particles. These atomized particles are essential for producing a compact ceramic base, or biscuit, which will be pressed later. The spherical shape of the dust particles allows them to fill the mold more efficiently and aids in the pressing process, where they are compacted to form tiles with the required mechanical strength. At Gaeaforce, high-pressure presses are used to compress the atomized dust vertically, breaking the granules and reuniting the original particles from the milling process. The water content in the mix facilitates the binding of the particles, resulting in tiles that are strong enough for the subsequent steps. After pressing, the tiles retain a small amount of moisture and need to be dried. This is done in a horizontal dryer, where the tile's residual humidity is reduced to around 0.5%. Complete drying is avoided, as fully dried tiles become fragile and could easily break during the following mechanical actions, such as glazing and decoration. The glazed surface gives ceramic tiles their aesthetic appeal and protective properties. In this step, tiles move onto the glazing line, where multiple layers of slip, a liquid mixture of clay and water, and glaze are applied. An essential component in this process is the engobe, a material placed between the clay base and the glaze to improve the adhesion and overall finish. Gaeaphors employs cutting-edge digital ink injection technology for decoration. This method allows for contactless ink injection, covering the tile's entire surface with high precision, even in areas with relief. The factory's advanced printing machines operate with pentachrome, allowing for high-resolution printing, up to 400 dpi, and enabling the customization of tiles with a variety of designs, including stone, wood, rustic, and marble effects. The digital system also reduces waste and allows for quick adjustments in tile designs through digital file changes. In addition to ink injection, Gaeaphors integrates rotary printing and rotograver techniques to apply other materials and decorative effects. The glazing and decoration process not only enhances the visual appeal of the tiles but also imparts essential properties such as impermeability, resistance to chemicals, non-slip surfaces, and easy cleaning. The firing stage is perhaps the most crucial step in the ceramic manufacturing process, where tiles undergo significant physical and chemical transformations. At Gaeaphors, tiles are fired in single-layer roller kilns using rapid firing cycles, which last between 45 to 60 minutes. The kilns, which are powered by natural gas, reach temperatures between 1,100 and 1,200 degrees Celsius. The firing process occurs in a long kiln chamber, which is around 110 meters in length and 2.5 meters in width. The tiles are subjected to direct heat from the flame, which is efficiently managed to minimize fuel consumption. The kilns are designed to optimize heat recovery by reusing the hot gases produced during firing to preheat the tiles at earlier stages, resulting in energy efficiency. This rapid firing process enables Gaeaphors to produce a large quantity of high-quality tiles in a short period. Once the tiles are fired, they are subjected to a thorough sorting process, during which quality control is performed to eliminate any defective pieces. The first step in this process involves visual inspection of the tile's surface by artificial vision machines, which check for design and color inconsistencies. Operators then manually inspect each tile to ensure it meets aesthetic and quality standards. The tile's dimensions, including flatness and size, are also measured using precision equipment to guarantee uniformity. Consistency in size and flatness is crucial for the tile's industrial use, as they must comply with specific standards. After the quality control checks, the tiles are sorted and packaged for storage. The factory's products are then distributed to over 90 countries, reflecting Gaeaphors' global reach in the ceramic industry. Brick has been a fundamental building material for thousands of years, with its production methods evolving dramatically over time. From ancient hand-molded techniques to modern automated systems, brick production technology has improved in terms of efficiency, quality, and sustainability. This article delves into the history of brickmaking, the introduction of mechanization, innovations in brick kilns, and the future trends in the industry, focusing on the use of advanced materials, environmental impact, and automated manufacturing. Early brick production, a manual process. The use of bricks dates back to around 7000 BC in what is now southern Turkey and ancient Mesopotamia. These early bricks were simple sun-dried mud structures, primarily made from clay mixed with water and shaped by hand or using molds. Sun drying was the only method of hardening these bricks, which limited their durability and made them vulnerable to weathering. This technique persisted in many regions until around 3000 BC when fired bricks began to be produced.
Para quitarle el canto que le queda en el suelo, como el cuchillito ese así, ese canto que grande que tiene o uno pequeñito para que el ladrillo quede cuadradito para cuando uno lo vaya a coger, a meter en el horno, no tenga ese canto.
Fired bricks were initially developed in ancient Egypt and Mesopotamia, where the technology to control fire for creating stronger, more durable building materials was discovered. These bricks were typically fired at temperatures ranging between 600 degrees Celsius and 900 degrees Celsius in simple open kilns. Early kilns were crude, relying on wood or straw for fuel, which made temperature control difficult. As a result, the quality of bricks varied greatly, with some being overfired and others underfired. The Industrial Revolution and Mechanization, 1750 to 1900. The turning point in brick production technology came with the Industrial Revolution in the 18th century. By this time, the demand for bricks had risen due to rapid urbanization and the construction of large industrial and residential buildings. Hand molding could no longer keep up with this demand, leading to the mechanization of the brick production process. The first major breakthrough was the invention of brick-making machines. The first patented machine was developed by Henry Clayton in 1855, which was capable of producing up to 25,000 bricks per day compared to the manual method, which typically yielded around 1,000 to 2,000 bricks per day. Clayton's machine used a steam-powered piston to compress clay into molds, making it more efficient and consistent than hand molding. Around the same time, continuous kilns such as the Hoffman kiln were developed. Invented in 1858 by Friedrich Hoffmann, this kiln revolutionized brick production. The Hoffman kiln had a series of chambers that allowed for continuous firing, with one section cooling while another section was being fired, thus maintaining production without interruptions. This innovation improved the energy efficiency of brick firing by about 50%, significantly reducing fuel costs. Temperatures in the Hoffman kiln reached up to 1,100 degrees Celsius, allowing for the production of stronger, more consistent bricks. The 20th century, automation and scale, 1900 to 2000. The 20th century saw further advances in brick production, primarily in automation and scaling up production capacity. One key development was the extrusion method, first introduced in the early 1900s. This method involved forcing clay through a die to create a continuous ribbon, which was then cut into individual bricks. This process eliminated the need for hand or machine molding, increasing production speed and reducing labor costs. Extrusion machines could produce up to 40,000 bricks per day by the 1920s. Further advancements in the mid-20th century improved extrusion machines to produce up to 100,000 bricks per day by the 1960s. These machines also improved the precision of the shape and size of bricks, which were critical for large-scale construction projects that required uniformity. Brick kilns also evolved during this period. The introduction of tunnel kilns in the early 20th century allowed for a fully automated firing process. Tunnel kilns work by moving bricks slowly on conveyor belts through a long, horizontal kiln, where different zones are heated to different temperatures. This method, unlike the Hoffman kiln, allows for continuous and faster production while ensuring uniform heat distribution, which improved the quality of bricks. Tunnel kilns could reach temperatures of up to 1,300 degrees Celsius and could fire bricks in 24 to 48 hours, compared to the several days required in older kiln types. Modern brick production technology, 2000 present. Today, brick production is highly automated and energy efficient, with a strong emphasis on sustainability. The global demand for bricks continues to grow, with countries like India, China, and the United States leading the production. Current global brick production stands at approximately 1.3 trillion bricks annually, with China accounting for more than 60% of this total. Advanced automation. Modern brick factories are equipped with advanced automated systems that manage every step of the production process. From raw material preparation, mixing, and extrusion to cutting, drying, and firing, the entire process is controlled by computer systems. This automation has reduced the labor required in brickmaking, which in the early 20th century still required significant manual work. Today, a factory capable of producing over 200,000 bricks per day may require fewer than 20 workers, compared to several hundred in earlier periods. Energy efficiency. Energy efficiency has become a major focus in modern brick production. Innovations in kiln technology, such as hybrid and fuel-efficient tunnel kilns, have reduced the energy required to fire bricks. The average energy consumption for firing bricks has decreased by about 40% since the 1970s. Modern tunnel kilns are designed to reuse the heat from cooling bricks to preheat the incoming green bricks, thereby optimizing fuel consumption. One significant energy-saving technology is the use of lightweight bricks, which require less clay and energy to produce. These bricks have hollow cores or perforations, reducing their mass while maintaining structural integrity. In some cases, the production of lightweight bricks uses 20 to 30% less energy than traditional solid bricks. Sustainability and environmental concerns. The brick industry has faced growing pressure to reduce its environmental impact, particularly regarding emissions from kilns. The firing process releases significant amounts of carbon dioxide, and traditional fuel sources like coal and wood contribute to deforestation and air pollution. Many modern brick factories have shifted to using cleaner fuels, such as natural gas, which reduces emissions by up to 50%. In addition, manufacturers are exploring alternative materials to reduce the reliance on clay, which is a finite natural resource. Recycled materials such as fly ash, a byproduct of coal combustion, are increasingly being incorporated into brick production. Fly ash bricks are lightweight, durable, and require less energy to produce, making them an attractive alternative for environmentally conscious builders. Water-saving techniques are also being adopted in brick production. Advanced factories now recycle water used in the brick forming process, reducing the demand for fresh water, which is particularly important in arid regions where brick production is common. Future trends in brick production. The future of brick production technology is likely to focus on further automation, sustainable materials, and digitalization. 3D printing of bricks is one emerging technology that could revolutionize the industry. Using advanced 3D printers, custom-designed bricks can be produced with high precision, enabling architects and builders to explore new design possibilities. 3D printing also reduces waste by allowing for the production of only the exact number of bricks required for a project. The integration of smart technology into production lines is another key trend. Sensors and artificial intelligence, AI, are being used to monitor every aspect of the production process, from moisture content in the clay to temperature control in kilns. AI can detect anomalies in real time, reducing waste and ensuring consistent quality. Additionally, efforts to produce carbon-neutral bricks are underway. Some companies are experimenting with non-fired bricks made from materials like geopolymer or cement-based composites. These bricks do not require firing, which eliminates the need for kilns and drastically reduces the carbon footprint of brick production.